We're now going to try to blend from, or transition from, our study of contour diagrams to our study of derivatives. And we're going to do that by looking at a subset of functions of two variables, look at their contour diagrams, and look at what they tell us about slopes, which again is our key idea behind derivatives. We're going to be looking at linear functions of two variables, and the basic form of any linear function in two variables is intercept, slope in x, and slope in y. So these two values in front of the x, or the value in front of the x and the value in front of the y, can be interpreted as slopes in the x direction and slopes in the y direction. C would be the z-intercept. So if we take an example like z equals 2 minus x minus y, we would have two negative slopes, -1 slope in the x direction and -1 slope in the y direction. Now I do encourage you to try to build a function like that. This is a nice straight plane function, so you can mimic it with a piece of cardboard or something else that's flat, and try to put two slopes on it. It's worth noting what that shape would look like. If we do our standard three axes here, and we have slope -1 in all the directions, the graph is going to look like a plane, and this plane, if we draw it in this little octant of x, y, and z, it's the quadrant version of this is the 3D version of a quadrant, we would see a plane that moves down like this, and because of the boundaries, it sort of looks reasonable when we sketch it out on a piece of paper. And so what we just said here is that if we move in x, if we increase x, then we decrease z as a result. So x and y are definitely the inputs, and z changes as a result of a change in the inputs. And if we increase y, guess what happens? We decrease z because there's a negative slope associated with the y direction as well. Now it's getting a little bit ahead of ourselves, but I want to lay the foundation here. If we were to go down the x-axis, we'd have a slope of -1. If we were to go down the y-axis, slope of -1. If we were to go backwards on either of those, we'd be going uphill. So our idea about slopes are going to get a little changeable shortly. The other thing that we could do is not go along the x or y axes, and what we could do is sort of walk out this way. And as we're going to see soon, it's a steeper downhill slope in this direction. And notice that the direction is on the xy plane. So we can get something a little steeper, and again, this is easier to see if you hold up a book or something and make the two slopes of -1 and imagine splitting the difference, going between those two slopes. You'll see it actually has to be steeper in between than it is along the two boundary slopes you constructed this plane with. One of the nice things about functions is we can represent them different ways. Here we've got a table representation, and this is just a rehash of what we've seen with single variable functions. Linear functions in two variables are linear in y and linear in x, so all the nice rules about how tables are laid out will apply here in both directions, as we increase y or as we increase x. In particular, if we know that there's even steps here of delta y each, and we also notice there's the same delta x here, same delta x between points here, then we're going to get the same delta z as we move down this table. So if I'm at the point 1, 1, 2, I get a z value of 2. And if I take 3 steps down, I'm going to be at 8. I think it's pretty clear that the way I'm going to get to 8 is by even steps. It would be 2, 4, 6, then 8. Now, if we go the other way, we're also going to have changes in z because we changed x values. And here, that's a total gap of 15, which means each individual step has to be 7.5. So we end up at 13.5 in between those two. And same thing, once we're after the 21, we'd add 7.5, that'd be 28.5. And the wonderful thing about linear functions in two variables is once you have a row and a column, you can just fill the entire table in, whichever way you like. Every time I move down, I go up 2. Every time I move up, I go up 2, or down 2 rather. Or going left to right gives me an addition of 7.5. We can get these numbers whichever way seems easiest to us. I like the 2s because they're easier to work with. And last but not least, we can go up 2 here, down 2, down 2, and that would be up to 15.5. So this lets us define a function as a table, and we can complete it because we're told that it's linear. If it wasn't linear, all sorts of crazy things could happen, but we're told it's linear, so we know that this repeated pattern of every time I change y, I change z by the same amount. Every time I change x by delta x, I change z by the same amount every time, everywhere on the surface. That is a huge boon to the simplicity of the function. Now, what about a formula? Can we get a formula out of this particular table? Of course we can. We have all the information about the function here. Let's talk about the x-slope. Well, the x-slope is the change in z divided by a change in x. And we just said, well, if we take one step in x, we go up by 7.5. And the delta x is 1, so that slope is going to be 7.5. The y-slope is going to be delta z over delta y. So this is a maybe, well, this is certainly new compared to what we used to see with single variables. Delta y is in the denominator here, but that's because it's the input variable. So it always is what's the change in our output for a given change in the input. And we said the delta z, it would increase by 2 every time we take a step in y. But the steps in y are tiny this time. They're only 0.1 based on the values in the side of this table. And so we get a y-slope of 20. What does that mean in terms of our function? Well, we can write z is equal to, we certainly know the slopes now, 7.5 and 20. Now I'm going to write this in a different way than we saw before, but I think you'll see the analogy. We have a value. I'm going to pick this value here to start. We can pick any value as representative, but let's pick this one just because it's in the top left corner. Instead of c plus mx, we're going to have, let's call it z naught, x naught, and y naught. So we're going to have z naught, which is my base z value, and then I'm going to get changes in that with slope 7.5 when I increase x away from 2, or change x away from 2, and I'm going to have changes when I move y away from 1.1. So this would be what's typically called the point slope form, because it involves a point. It goes through, we have the slopes, and it's through the point x naught, y naught, x naught, y naught, z naught. The point intercept, or sorry, the slope intercept form is the one we saw briefly earlier. You can convert between the two. You just expand it out. 7.5 times negative 2. Heck, let's do it. The alternative would be 2 minus 15 and minus 2.22, minus 22, plus 7.5x plus 20y. And this form would be the slope intercept. Now everything's centered at x equals 0 and at y equals 0. Let me try to make that more legible. There we go. So this would be an alternative form. I don't care which one you use. I find this one usually easier to use because it can be applied in all situations. The intercept we don't often care about unless it's been given in the first place. So you're free to choose. This one's the most versatile, so I'd recommend it if you had to make a choice to start. All right. Now what can we do to tie this back to contours? Well, we have all these values, and let's do it out here. What we do have as values, let's do the x values, 2, 3, 4, 5. That's an x, and we'll put a little break in here. For the y's, we'll have 1.1. 1.2, 1.3, 1.4. I think that's all we had. Do we have 1.5? Nope, just those. Okay. So through this diagram, we don't see a lot of common ground, but we're looking for the z values. We're looking for points that share the same z value. So if we imagine the point 2 here, well, where else are we going to see points that are height 2? Not anywhere else nearby. Where else do we see more similar values? Right around here. At 5, 1.1, we're at 24.5. And down here, we're getting close to 24.5. We just have to go a little bit further. In fact, we have to go down to about 1.6, which would give us 25. And so somewhere in the middle is another point with 24.5. So let's take those as our anchors. 1.15 and 1.64. 1.15 and 1. Almost 6. Sorry, 1.6? 1.5 would be nicer. That would make a lot more sense. Keep our delta y's the same. And 1.54. So a little shy of that, about there. So the contour at height 24.5, there we go, would be here. And it would keep going, obviously. It would go on further past there. If we go and do the work, let's take a look at one level down from there. What about the 17 and the 17? Hey, it would show up about the same thing, but over 1. So we'd have another contour just shifted over by 1 of here to here. There we go. That would be 17. And then we'd have another contour after that. Well, guess what? It'll be the same relationship because we always have the same differences in x and y. 17 and what was that one? 17, 9.5. So we can see a pattern emerging here. These lines are all based on 2 points, 2 points, 2 points, 2 points that always have the same relationship to each other. And so we might come up with a nice hypothesis here that if we looked at all linear functions, so not just this particular example, but we can hopefully generalize from it, that their contour lines are straight lines, or their contour curves, contours are all straight lines. Those contour lines are all going to be parallel with one another. And they're also, these, as we see the parallel, I can imagine there'd be another one afterwards, another one after that, and they're evenly spaced. Again, assuming the z's are evenly spaced. But there's no change in slope, no change in steepness. So that's a nice consequence of our slope interpretation of the spacing of contours. There we go. So those features are going to come back and be of very significant use to us when we start talking about derivatives.